Hello there! In this lesson we'll look at double displacement reactions. In this little image you can sort of see a representation of what double displacement means. Basically it's a switching of partners, so you can just pick a cation or an anion, and if you switch spots with them, that's how you'll get your new products in a double displacement reaction. So it's two compounds where either the cation switch or anion switch, doesn't matter, you're going to end up with the same thing. And so you end up with blue with the purple and the green with the red. Just make sure you keep the positives and negatives together. Don't be combining negatives or positives. So this is a positively charged ion and negatively charged ion, and then this would be a positive and negative here. So this negative is going to go with the other positive, so you still end up with plus minus, plus minus. As long as you're not putting negatives together and positive together, you're good. So to show this in another way, without symbols, we have letters here to represent the displacements that occur, and you can think of these two as displacing each other, hence the term double displacement. So in the end, with this example here, we'll take the chlorine and we will switch it with the carbonate, right? Remember that these have different charges, so the new compounds you'll have to make sure you do crisscross to figure out how many there are. So carbonate has a charge of 2, and so that means you need 2 lithiums to go with it. And to go the other way, you're going to have magnesium with a charge of 2, and you're going to need 2 chlorines. And then you can balance as needed after that. So when you have double displacement reactions, there are various products that can form. And so we're going to group them according to whether you get a new solid. That's what we got over here. You can see there's kind of a flaky solid kind of in the bottom there. So solid. You can get a new liquid. So over here we took 2 solids and mixed them together, and this is a new liquid that forms. And then of course you can get gases as well. So we're going to divide them up according to what sort of products you end up with. So the first bunch we're going to look at here are the ones that create gases, right? And so you can start off with the classic baking soda and vinegar, which follows this pattern. So if you do double displacement with baking soda and vinegar, you can see that if you just write it out as double displacement, it doesn't really take into account the gas that is formed. So you can think of double displacements that form gases, some of them anyways, as being sort of a double displacement and then a little decomposition that follows. So if we say displace this with this, right? So you get the positive, sorry, this is the negative. This time this is the positive, this is the positive, and this is the negative. So if we put them together here, we're going to end up with sodium and then the acetate, 3COO. And then you're going to have H2CO3. Now it doesn't stay that way because we all know that you get bubbles when you mix baking soda and vinegar. So really what happens is it's water and carbon dioxide. So if you see H2CO3 as a product, you should break it down into these products, and there's your carbon dioxide gas as one of the products. So these other ones here follow pretty much the same pattern. So if you take a sulfite and put it with an acid, you will get the same thing. So it'd be sodium with the chlorine, and then instead of H2SO3, you'll break that down into H2O and SO2. And there's your gas. And then with ammonium and hydroxide, it's pretty much the same thing. So you end up with the NaCl from these two, and then you'll have NH4OH, which is not stable and doesn't stay in solution, and you'll end up really with the NH3 gas and some water, right? The last one here actually does give you a gas right away. It's if you have sulfides. And so again, you're going to get the sodium and the chlorine. They're going to go together. And then the other two that go together would be 2 hydrogens to balance out a sulfur. And that's a gas all by itself, so you don't need any decomposition for that guy. All right, so those are the only ones that we're going to use. The sulfur dioxide, which is just like the carbon dioxide. Then we got ammonia, and we got hydrogen sulfide, which is a stinky gas. So as a summary, you can look for carbonates to give you a clue that maybe carbon dioxide is a product. You can look for sulfites, and that'll tell you that maybe sulfur dioxide will be a product. You can look for ammonium ions. That would tell you that maybe ammonia is a product. And sulfides could lead to hydrogen sulfide gas being produced. So these are all gases that are commonly produced in double displacement reactions. All right, so neutralization are the only reactions we're going to bother with that produce a liquid, and that liquid, of course, is water. So whenever you have a base and an acid, that reaction will be a neutralization, right? They balance each other out, and you can neutralize one with the other. So what happens is that the one ion, the metal, and the one from the base is going to go with the non-metal from the acid. You get magnesium chloride, and that is the salt. And then the other parts, the OH from the base and the H from the acid, that's what's going to make the water. And of course, you have to balance things out here in order to get it all to work. But that's always the same two products with neutralization. You get an ionic compound, which is also called a salt, and you get water. Oh, a little joke for you. What is this? We'll say MgOH2, MgCl2. The joke is the base is under a salt. All right, there you go. Good times. All right, so neutralization are easy to pick out as long as you can identify your acids and bases. Acids, of course, are going to have hydrogen with polyatomic ions or some of those organic acids that you learned about. And bases, the ones that we're going to use, are all going to be hydroxides. And so we can do double displacement with all these and see what we end up with, and then see if we can identify which ones are neutralization. So this here is definitely an acid, and this here is a base. So this one's going to be neutralization. We're going to get lithium sulfate and the water. Lithium sulfate is the salt, and water, of course, is water. And then for this next one, we see that we have a base, but we don't have an acid. Sodium carbonate is not an acid. So we can do a double displacement, but it won't be a neutralization. We'll end up with sodium hydroxide and lithium carbonate. And then you'd have to, balance things out here in order for it all to work. The last one here, we have OH here, so that's a base. And we got hydrogen with the carbonate, so that's carbonic acid, so that's an acid. So yay, we got neutralization again. And this time the salt will be Fe2CO3 bracket 3. And we'll also end up with some water. And then, of course, we've got to balance all that out. We got 2 ions, so 2 here, 3 carbonates, so 3 here, and 3 times, end up with 6 waters. Yay! So neutralization will be this guy and this guy, the ones that made the water. Finally, when you are doing neutralization reactions, of course, water is clear and colorless, and most of the solutions that you're going to use are clear and colorless to start with, and so you'll need to use an indicator to show that you have neutralized your acid or your base. So here's one that I made at home. This is a hibiscus plant that we have that grows outside in the summer, and we bring it in the winter. And sometimes it makes a lot of flowers. So I took a whole bunch of the flowers and I put them in a pot here. After they bloom, they fall off after a day or two. And I boiled it. And once I boiled it, I got this nice solution that is kind of a light purple, right? So this is a neutral solution of all these hibiscus flowers boiled in water. And then I took some base, which is household ammonia. This is what we use for like cleaning glass around our house. And some acid, some vinegar here. And when I put the vinegar in, you can see that it turned this nice red color. And then when I put the base in this side, you can see it turned a darker purple. So this means that the pigments that are in the hibiscus plant are acting as an indicator. It can show you whether you have something that's more acidic or more basic based on the color. One that we often use that's really neat because it has a nice clear turning point where it goes from one color to another is phenolphthalein. So phenolphthalein doesn't have any color when it's in an acid or if it's neutral. And then if you when you are using it in a neutralization, if you just go to slightly basic, so just after the neutralization point, it turns this nice bright pink. Yeah. So it's really useful in when you're learning about titration, and it has a nice distinct color when it's in a base.